Consider the system y is equal to 2x plus 3.75 and 5x minus 2y is equal to negative 9.5. Determine how many solutions the system has, and then classify the system as consistent or inconsistent, and the equations as dependent or independent. So let's just review a little bit what all of these words mean. So let me draw the different scenarios we can have when we have two equations with two unknowns, or we have two lines in two dimensions. So I'll draw them up here actually. I'll draw them relatively small. So that's my y-axis. That is my x-axis. So it's y and x. Let me copy and paste this a couple of times. So let me copy and paste it. That's one scenario. That's another scenario. And then let me paste the third scenario. And let me draw out the scenarios. All I've done so far is I've drawn the axes. So I could have one scenario where I have two lines in the two-dimensional coordinate plane, and they are two different lines, and they intersect in exactly one point. So that could be one point, that could be one line, that could be the other line. Then I could have two lines that are two separate lines, but they never intersect. And they never intersect because they have the exact same slope, but different y-intercepts. The different y-intercepts is what allows them to be different lines, different but parallel lines. And then these obviously will never, if a system of these two equations or these two lines will never intersect, because parallel lines never intersect. And then finally, you could have a scenario where both equations are essentially describing the exact same line. Now, depending on whether you look at the equations or the system itself, there's different ways to label these things. So if you look at the equations themselves, so from an equations point of view, these two equations are clearly two separate lines. They are not the same lines here. So we call these two equations as being independent. The equations that these lines represent these two lines are also two separate lines. They are not the same lines. So once again, we say the equations that these lines represent are once again independent. Here, the two equations represent the exact same line. So here we're talking about a dependent equations. So these are independent equations, dependent equations. Now, it becomes slightly different, or we use slightly different words when we think about the system. And when you think about the system, you care more about the number of solutions that you might have. So here, when you have exactly one solution, this is consistent. And a consistent system has at least one solution. Consistent. So this clearly has one solution. This has an infinite number of solutions. Any point here will be a solution. So this is also consistent. Consistent has at least one solution. And this right over here, these are two different lines that never intersect. It has no solution, no common point for both of these lines. So this is inconsistent. Inconsistent. So over here, a system that describes lines like this would be consistent. A system that describes lines that are essentially the same line would be inconsistent. A system that describes lines that are essentially the same lines would be consistent, because here you have an infinite number of solutions. Here you have one solution. Here, this system is inconsistent because it has no solutions. When you look at the equations, the equations that are represented by these lines are independent. The equations that are represented by these lines are independent. The equations that are represented by these lines are dependent because they're essentially the same line. Now, with that out of the way, let's actually talk about this problem. Determine how many solutions the system has and then classify. So the one way to think about it, this top equation is already in slope-intercept form. We know its slope, and its y-intercept is 3.75. We can essentially put the second equation to slope-intercept form and see how its slope and y-intercept compare. And if it has, let's compare it, and then we'll think about which of these three scenarios it falls under. So let me write 5x minus 2y is equal to negative 9.5. I want to isolate a y on the left-hand side. So let's subtract 5x from both sides. And so my left-hand side becomes negative 2y. My right-hand side is negative 5x minus 9.5. Now I can divide both sides by negative 2, to divide all the terms by negative 2. And I get y is equal to negative 5 divided by negative 2 is positive 2.5x. And then 9.5 divided by 2 is 4.75. The negatives cancel out, so plus 4.75. So I just rewrote the second equation in slope-intercept form. Its slope is different than the first equation. This first equation has a slope of 2. This one has 2.5, and its y-intercepts are different. But the slopes being different, that by itself is enough to know that these are going to be two separate lines that are not parallel. If the slopes were the same, then we're saying, okay, we're either dealing with parallel lines or the same line. But since the slopes are different, we know that we're dealing with two different lines that are not parallel. So we're definitely dealing with this scenario right over here. So these equations are independent, and this system, when we look at both of them together, this system right over here is going to be consistent. We will have exactly one solution. So this, when we know, since they have different slopes, we're dealing with this scenario, we are going to have one solution, which makes it consistent. If someone told you that a system was consistent, that by itself isn't enough to say that it has exactly one solution. Consistent tells you it's at least one solution. You'd be dealing with this scenario or this scenario. The reason why we know it has one solution is that the slopes are different, 2.5 versus 2. The slopes are different, so we know we're dealing with this scenario right here. Two non-parallel lines that are not the same lines, and they will intersect in exactly one place and have exactly one solution. I should point to that right over there.